Okay, here we go. Algebra 2 midterm review. This is going to be part 2. In the last video, we really looked at unit 2, where we were discovering quadratics, graphing them, kind of reasoning through the different variables and values that we're looking for, the characteristics, such as the vertex points, the x-intercepts, the y-intercepts, axis of symmetry, that kind of stuff. In unit 3, we get to a point where we're asking questions about how do we do some of these things a little easier. Here on the screen, you can see stuff in green. That's the stuff that's super easy to find. The stuff in yellow, we have figured out ways that we can reason our way to those values. And if we look at standard form, notice that there is an item in red, particularly P and Q, those x-intercepts. When we were given a standard form quadratic, there was no way to find those other than guessing and checking. We don't like that. We want a better way. We want a better way. In the last video, we talked about how we can go from vertex form to standard form by multiplying binomials and simplifying down. We also looked at intercept form and how we can do the same thing. We can multiply our binomials and convert to standard form. Now, vertex and intercept form are both pretty strong. There's some stuff that we have to reason through, and by converting to standard form, it gives us another way to check some of our values, especially C, because we're given C in standard form. But when we are given standard form, it'd be nice, it would be super, super nice to be able to get P and Q exactly. Well, when we look at these three forms, which form is P and Q the easiest in? Of course, that one is intercept form. So we want a way to go from standard to intercept. We want to be able to convert those. In fact, by going one direction and multiplying binomials, we've unlocked how to do this. Here is an example. We have y equals x plus 4 times x plus 6. This is intercept form. We knew that we could multiply our binomials. So we get x squared plus 6x plus 4x plus 24. We combine our like terms there in the middle, and we get plus 10x plus 24. Brilliant. We have just gone from intercept form to standard form. But what if we wanted to go backwards? I want to point out a pattern here. Look at this 24. 24 is just 4, the term that we saw here, times 6, the term that we saw here. And in fact, when we look at 10, B in our standard form, we notice similarly it is 4 plus 6. If you take a second to study what's happening when we FOIL and you look at kind of the terms that line up, you'll see why this is happening. But this tells us, well, hey, C is going to be the product of the two numbers that we put in those groups, and B is going to be the sum of those two numbers, and it has to be the same pair of numbers. Now let's take a look and see how we can go from standard to intercept using this same knowledge. Let's see, C is 36. I know that that has to be the product of two numbers. I've got a bunch of numbers that can get me there. 2 and 18, 3 and 12, 4 and 9. And in fact, I could do the negatives of all those. I could do -1 and -36 as well. But I do know that that pair has to add up to 15 as well. So as I look at my pairs, I'm looking for a pair that adds up to 15. And well, one of them stands out, 3 and 12. Those two do add up to 15. So pretty quickly, I was able to figure out, well, hey, x plus 3 and x plus 12 is the intercept form of that original function written in standard form. And if you were ever curious about how to check your work, you could always do your FOIL back out, and you would get x squared plus 12x plus 3x plus 36. And of course, your 12x and 3x would combine to 15x. So right there, we've checked our work and everything looks good. And it is as basic an idea as that. We are just asking ourselves, how can we find a pair of numbers that gets us C and B? C will be the product, B will be the sum. Now again, what does this help us do? Well, it gets us our x-intercepts really quickly. There's two ways that we can look at it. Well, hey, if y equals x plus 3 and x plus 12, we knew that our intercept form was x minus p and x minus q. And so looking with this form, we do have to be careful about the sign, but we can see that p would actually be -3 because x minus p, x minus -3 would be x plus 3, and q would be -12. But the idea here, if you're looking for something conceptual, the idea here is that we are looking for our x-intercepts, and the x-intercepts exist when y equals 0. If we're looking at a graph, it will cross the x-axis when y equals 0. So we can look at this as y equals x plus 3 times x plus 12, and know that, well, hey, if we're finding x values that find us our x-intercepts, we can actually get rid of this y, and we can replace it with 0. Now this relies on something called the zero product property. And all that property states is that if I have two numbers, a times b, and they equal 0, well, in fact, one or both of those two numbers has to be 0. There's no way that we can multiply two non-zero numbers and have the product be 0. And so what that tells us over here is, well, hey, I've got some number inside of this group, whatever that ends up being, and some number over here. So one of those has to be equal to 0. And in fact, we'll find that, well, hey, in the situations where one or the other one is 0, we'll have our x-intercepts. So we can look at x plus 3 equal to 0, and we can look at x plus 12 equal to 0. And just using our Algebra 1 skills, just to move stuff from side to side, we can see that x equals -12 and x equals -3. We might call one of these p, we might call one of these q, and in fact, if we look up at what we had figured out before, those are the same things that we found. If you can reason through this form, and a is equal to 1, that's not too bad to do. But understanding that this 0 is the key that unlocks how to use this and why this works, we can solve more complicated problems. Let's see a few. Now, these might look familiar. These are the ones that we did in class. If you're looking to follow along, finding zeros of trinomials and binomials is the name of the worksheet. It was printed on green paper, I do believe. So let's just work through a couple examples. These are the kinds of things that you would see. This first one, we've got -45. It's negative instead of positive, but we can still do that. -45. We have -1 and 45, 1 and -45. There is, I see 3 and -15, -3 and 15. I also see 5 and -9 and -5 and +9. Now, of course, I'm also looking for a pair that adds up to -4. And as I look through this, I see positive 5 and negative 9 as that pair. So what I can actually do is write out, well, hey, in intercept form, this is just going to be x plus 5 and x minus 9. To find our zeros, we would just set this whole thing to 0. Which tells us that x plus 5 could be 0, or x minus 9 could be 0. So our x-intercepts are negative 5 and positive 9. Those are our x-intercepts, or what we might refer to as our zeros. Let's look at the next example. Let's kind of box this one off because we're done with that one. The next example. Okay, well, this one looks a little bit different. Does look a little bit different. We see our a term out front here, x squared. We see our c term out here, negative 81. But we are missing that middle term that usually has a b times x. Well, in fact, if we see that missing, we know that, well, hey, b is just 0, because 0 times anything makes it go away. So we actually have this 0x in the middle. But we do the same steps. We say what numbers get us to negative 81. I'm seeing 1 and negative 81, or negative 1 and 81. I know right away, well, hey, 9 and negative 9, that's a pair that would work. And I believe we could do 3 and 27, 3 negative 27, or negative 3 and positive 27. So there's a couple options. But again, we have to ask ourselves, well, hey, these have to add up to b. And in fact, the only one that will work here is 9 and negative 9. And in fact, we'll see this kind of pattern as we see b go away in any problem. If b is 0, well, that pair of numbers are going to be equal but opposite. Equal but opposite. And so we can write this as intercept form by writing x plus 9 and x minus 9. Set it to 0, because we're finding our zeros. We're trying to find our x-intercepts, and that is where y is 0. And so x plus 9 or x minus 9 equals 0. And this is a pretty easy one because they jump out just like that. Boom. There are those. Let's close this one off. We're making some good progress. Take a look at this last one. We have a couple things happening here. Well, b is gone. B is gone. So we can rewrite as 9x squared plus 0x minus 49, if that's helpful to visualize. But we also have this 9 right out front. This 9 here is making things a little bit difficult. But we'll see what happens. We'll kind of like think about this step by step. Let's look at 49, because the first question is, well, do I have any pairs that get me to negative 49? I know 1 and negative 49, negative 1 and 49. I know 49 from my times tables because that's 7 times 7. And so one of these could be negative. And in fact, just like we said, well, hey, that's what we're looking for. We're looking for them to be equal and opposite if b is 0. So now, as I think about my intercept form, I know it's going to look like this. I know that my numbers here and here will be 7 and 7, plus and minus. I know there's an x there. But something's going on to make this 9 pop out in the front. I've got to take account of this 9. It's no longer 1. This 9 will pop up when we multiply these two terms for FOIL. So we can think about, well, hey, what numbers would go in front of this x to make it 9. We'll move those just so they're not in our way, but what numbers add up to, or multiply to 9? 1 and 9, 3 and 3. Those are possible options. We can go negatives as well, so we could do negatives of those and the positives. But I want to point something out. Yes, we're going to multiply the first terms, but we're also going to multiply the outer and the inner. So we're multiplying the outer and the inner. And this is how b goes away. B goes away because 7 times x gets us 7x, and negative 7 times x gets us negative 7x. And so because those are equal and opposite, that middle term goes away. So in fact, we'll notice, well, hey, whatever we put here and whatever we put here is going to be multiplied into each of those. So those actually have to be the same as well. So when we're looking at 9, we see, well, 3 and 3. 3 and 3 get us there. So we have 3x plus 7 and 3x minus 7. This looks a little weird. If you were ever questioning it, you could definitely refoil. You could foil this back out and you would see what happens, which is very cool. But we want to find our zeros, so we're just going to do 3x plus 7 times 3x minus 7 gets us 0. So 3x plus 7 equals 0, or 3x minus 7 equals 0. And with our algebraic steps, we would subtract 7 to one side here, and we would divide by 3. So we get something a little strange, negative 7/3. And over here, we would get positive 7/3. And those would be our answers there. All right, let's bump this one down a little bit. Okay, take a look at this one. We have b didn't go away. We've got 70 here. And something could jump right out at you is like, we might have a problem here, but let's work through it. 1 and 70, maybe 2 and 35. I see 5 and 14, 7 and 10, working through all these possible combinations, and yet I don't see any of these adding up to negative 4. So this is where we would look out front. We would look out here to this negative 2. Notice that we've got this number here. That one cannot be squared either, so we can't fall back on the problem we just completed. But I do see that, well, hey, 2, 4, and 70, those are all equal, so I could perhaps pull a negative 2 out. I could pull a negative 2 out. And I could write this as y equals negative 2. And now I've divided everything by negative 2 to be able to do this. It's kind of like undistributing. So I've got negative 2 divided by negative 2 is just 1. Negative 4 divided by negative 2 would be positive 2x. And 70 divided by negative 2 would be negative 35. If you take a look real quick, you'd notice, well, hey, if we distributed that back in, we'd get right back to where we were. Oops. So now we have to look at this stuff in the group. We can erase what we were working on before because we're not working with 70. We've taken a factor out of that. Now we are working with negative 35. Let's see if that one yields any results. 1 and negative 35, negative 1 and 35. I see 5 and 7. One of those has to be negative. 5 and negative 7. Oh, I think we found it. I think we might have found it because we're looking again for something that adds up to positive 2, and I see that pair right there. So we can write this as y equals negative 2 out front, and then our two factor pairs, as we call them, x minus 5 and x plus 7. There we go. Now we might ask, well, hey, we've got this extra term out here. When we set this thing to 0, what's going to happen? We got 0 equals 2 times x minus 5 and x plus 7. And in fact, yeah, now we've got 3 terms multiplying each other. I'm just going to scoop this up a little bit. Let's think about this. Well, we've got 2 times some number times another number. Well, 2 can never be 0. So we don't really have to actually think about this 2 out here. We really just have to think, well, either x minus 5 is 0 and making this whole thing 0, or x plus 7 is 0 and making this whole thing 0. So in fact, we find our x-intercepts, or our zeros, are x equals -7 and x equals 5. So sometimes we have to factor something out. Nice. Let's look at another one. This one, we see b is gone. B is gone. And I see somewhat right away, well, hey, -75 does not have a square root, or not a nice one. So 75, there's no way that I can find 2 numbers that multiply to that and add to 0. Closest I could get was 9 and 9. That gets me to 81. And 8 and 8 gets me to 64. So 75 does not work out. But I do notice that, again, both of these are divisible by 3. So I can take a 3 out and notice that I've got, let's see, 75 divided by 3 is 25. So now I've got this 3 that I've taken out, and now I can think about 25 instead. And 25 is nicer to work with because I notice right away, well, hey, 5 and -5, that's got like a nice kind of almost a square, a difference of squares almost. So rewriting this as intercept form, I've got x plus 5 and x minus 5. Once again, we set it to 0. We can ignore this 3 out front. We can say, well, hey, either x plus 5 is 0 or x minus 5 is 0, which gives us x-intercepts of -5 and 5. Boom. One more to go. One more to go. Okay. Right away, boom, I see, hey, well, 7. I can't think of any numbers. There's no square of 7 or perfect square of 7. There's no number out here. B is gone. And in fact, this one is what we would call unfactorable. Unfactorable. If the approaches that we just used in the other 5 problems do not work, it is unfactorable. If we can't take out a greatest common factor from one of these, if we cannot find a root and that b term is gone, this one is unfactorable. Now that doesn't mean that we can't set it to 0 and just kind of think about what might be a way to figure out what x is. We can do this. We can set it to 0 because we know, well, hey, that intercept, the x-intercepts are going to exist when y is 0. Let's see if we can get x by itself. I'm going to add 7 to both sides. So I get 7 equals x squared. And how do we undo a square? Well, we square root both sides. So let's do that. Let's do square root of 7 equals the square root of x squared. And we find, well, square root and square goes away. So we have square root of 7 equals x. Now, of course, whenever we take the square root of something, there's going to be a positive and a negative root. That's something to always be mindful of. And in fact, if you put this into your calculator, you would find some kind of like long, non-ending, it kind of goes on forever, what we might call irrational decimal. So we have a positive and a negative, what is that, 2.645, and that would go on forever. That's one way to write it, but in fact, we want to be more exact. We want to be as exact as we can. So we would write the answer just like this. We would not do this out because it is not exact. It can never be exact because that decimal goes on forever. If it's helpful for you to think about, well, I normally have my two x-intercepts, you can write this as x equals the positive square root of 7 and x equals the negative square root of 7. That's acceptable too. But as usual, we do try to write things as simply as possible so that plus and minus up there is enough to tell me that there are 2. All right, that is everything. We'll talk more about this as we continue the unit after the midterm, but this will be the bulk of the work.